Hello, everyone. Thank you very much for your time. We appreciate that you were able to join us today for this webinar on the PLECS State Machine block. My name is Vitalik Ablayev. I'm a sales engineer at Plexim, and today I'm going to give you an overview of the state machine block found in our simulation software called Plex. Here is the outline of what I'm planning to cover today. If you have any questions during the presentation, please enter them in the questions window of the GoToWebinar control panel. And we will try our best to answer them during or after the presentation, or we'll get back to you by email. You can also always email us after the webinar at info@plexim.com. Let's begin with a few words about our company. We are originally a Swiss company. Our headquarters is in Zurich, Switzerland, and we now also have US offices in Boston and Seattle. We've been selling our simulation software Plex since 2002, and more recently came out with our own hardware-in-the-loop simulation platform called the RT Box. We have academic and industry customers in many areas where power electronics is being researched and developed. For those of you who have never used the tool, Plex is a system-level simulation tool for large power electronics systems. This slide uses one of our demo models as an example of what you can model in Plex. This model in the middle is a double-fed induction generator whose stator side is connected to the grid via a transformer, and rotor side is connected to a back-to-back converter. This model shows our different physical domains interacting with each other. The electrical circuit in black, mechanical drivetrain of the turbine in purple, thermal loss measurements in blue, Y delta Y transformer in brown, and the controls in green. The best way to get started with Plex is by using a trial via the link displayed on the slide. Once you install Plex, you will find this and many other models in our demo model library under Window Demo Models. Now let's briefly discuss the highlights of what a state machine is. A state machine is an incredibly powerful tool which can be used to control, model, and predict a system behavior. A different way of putting it is that a state machine is a convenient structure to represent a process, or a set of procedures which evolves over time, so there's always an evolving answer. An example of a state machine can be a program with sensor readings as inputs and control commands as outputs. Another example would be using a state machine to analyze a system and output some simple measure of its status, like whether it will converge to a steady state or diverge, or what's the state of a spacecraft, which valves are open or closed, what the levels of fuel and oxygen are, etc. In power electronics, state machines could be used for a variety of things, including supervisory controls and complex modulators. It's true that many problems could be solved using the recursive, functional, and object-oriented programming approaches, which you would use our C-script and DLL blocks for. For some complex problems, however, rather than trying to keep track of all of your indices for large nested loops, it makes more sense and saves you time to focus on graphically defining functions using a state machine. What's also important to mention here is that none of the coding languages allow us to keep the notion of internal state as easily as the state machine does. This could be useful if we want to keep track of the evolution of a system or keep track of the data which has accumulated over time in that system. State machines then are a method of modeling systems whose output depends on the entire history of their inputs, or systems with memory. With this new block, Plex lets you create graphically and edit state machines using common concepts such as boxes for states and curved arrows for transitions, and simulate them together with the surrounding system. Now let's go into the tool to show you around the state machine block itself. So I have the state machine block already pulled out onto the graphical schematic window here. For those of you who are new, this is the schematic window where the modeling happens, and this is our library browser where we find the components. If we double-click on the state machine block, this opens a graphical editor window where you can create states, junctions, and transitions. To create a new state, click on the Create a New State button at the top here in the toolbar, and then click anywhere within this window to place this state. A state is represented by a box with these rounded corners, and the name of the state is displayed at the top of the box. You may resize the state by dragging the corners of the state, as you can see here. You may also rename a state by double-clicking on its name here. To edit the actions associated with this particular state, you may double-click on the free area within the state. This will open a tabbed code editor in which you can specify the enter, during, and exit actions in the C programming language. The enter and exit actions get executed during the time step when the execution flow enters or exits this particular state respectively. And then the during action is executed during the time step whenever the execution is within whenever the execution flow remains within the state. If there is enough space, as here, then the code that you've written here is also displayed on the state on the schematic level here as well. And it's then directly editable from the schematic level. To duplicate an existing state, you may hold down the Control key or Command key on Mac, then click on the title bar of the existing state, and then drag the mouse to a new location in the same or different editor. So now I've created a duplicate state here. It turns out that states can also be hierarchical in Plex by containing other states. So to create hierarchical states, you may move one state onto another. So in this case, I would have to enlarge one of them and then drag this one over. This is now considered a hierarchical state where this state is called a superstate or a compound state, and the contained state is called a substate. This is the state 1 here is also then called a leaf state because it doesn't contain any other states. Compound states do not have a during action, so if I go into the parameters here, you will see that it's grayed out. And this is because intrinsically, in the hierarchical state machine, only the leaf states can be active, although the superstates here are implicitly active as well. So let me create another duplicate copy of this to talk about transitions a little bit. Transitions are represented by curved arrows from one state to another, or also the same state. So you can create transitions by clicking and dragging the arrow from one edge of the state to another, like so. So I just created one transition. Let me create another transition, and maybe another one from this substate to this compound state. You can change the start and end point of an existing transition by dragging it with your mouse like so. You may also change the way the transition is routed by clicking here in the middle of the transition. A double click on the transition opens the transition editor. This allows you to edit the priority, trigger, condition, and action of this particular transition. The transition with the lowest priority gets to be executed first over the other one, so it's given precedence. And it's also displayed on the schematic level you see here. So we have 3 transitions going from the same state to another state, and essentially they have different priorities here, 1, 2, 3. In the case when potentially there could be a transition taken during the time step from a substate or from the superstate, then we have to distinguish the precedence, which transition actually gets executed at that time step and which one is left out. So there could be a time moment where either this one could be taken or this one. So you see that they're both 1. So they're not distinguished by the precedence that way. So in this case, we actually have a hierarchical transition order option in the configuration dialog of the state machine, where the options are either top to bottom or bottom to top, where the leaf states are considered to be the bottom. So the default option, I believe, is top to bottom, in which case this is the transition that would be taken and not this one. So the transition from the top state is given precedence versus the transition from the bottom state. Let me open another model here. Plex distinguishes between explicit, time-based, and implicit triggers. You see, I've created examples for all 3 of these here at the top of this model. An explicit trigger is an input signal that's configured as a trigger signal. It is active whenever the input signal changes in a specified way. Here, this event E is active whenever the signal connected to the input terminal E toggles between 0 and non-zero. Essentially, this then populates a little port here where this is driving this particular transition. So if state 1 is active at the time, the transition fires or executes. This input signal only changes at discrete instance, but the variable time step solver still makes a step at the toggling instant. Next, we have time-based triggers, which are expressions of the form after and then the delay period, where the delay is an expression that evaluates to a number. If the state machine uses a continuous sample time, the trigger event will be created exactly t delay seconds in this case after the source state of the transition was entered. With a discrete sample time, the trigger event will be created at the first execution time following the delay period. So, and then we have an implicit trigger, which is a relational expression. So this will be active at the time step when the expression becomes true. So when it is evaluated to false in the previous time step and evaluates to true in the current time step. Essentially, this transition will evaluate to true at the step when x becomes greater than 0. The trigger, condition, and action combined form this type of a label that you can see here. So we have all 3 of them specified: x greater than 0, x greater than 1, and n equals to 1. And this is what they would be displayed as here. You may then edit them directly from the schematic window here. You may also actually change the positioning of this label if you're interested to. And one important distinction that we should talk about here is, notice the fundamental difference between an implicit trigger, which is x greater than 0 here, and a condition, which is also x greater than 0. So if we double click here, you see that the x greater than 0 is listed as a trigger, and here it's listed as a condition. So the big difference here is that the trigger will evaluate to true only at the moment when the value of x becomes greater than 0. So essentially that's the trigger. But this transition will evaluate to true whenever x is greater than 0. So at any time step, whenever x is greater than 0. And this is kind of the big difference here. Something that's also possible, of course, here, for those of you who are used to Plex, are the annotations, which can be entered by double-clicking anywhere in the schematic and then entering some sort of text that stays there afterwards. The other possible buttons we have up here are a default transition, which basically defines where the simulation should start, from which state. So you get one of these by clicking on this button, then clicking anywhere in the schematic and pointing to the first state that you would like the state machine to start from. And this basically decides the precedence of which state is first. And we also have a component called a junction, which is actually new in Plex 4.1, which basically defines the precedence of multiple states if the execution flow depends on other parameters which are decided in your model, in your actual Plex model, then you can essentially have an initial transition pointing to this junction block first, from where you can basically stem transitions from one state or another or multiple states. And then this will be decided where the flow goes after that. The state machine configuration is accessible via this button here. And if you click here, you see that Plex lets you define inputs and outputs, which then appear on the block itself. On the top level here, we see that we have an input E defined here for our trigger, and that's then displayed on the actual state machine block. And we also have constants, which remain constant during the simulation. We're able to define variables, which can be modified by the actions within your state machine, and these have to be valid MATLAB expressions. We also have C declarations, which could be global definitions, standard library headers, static helper functions, and macros such as current time in this case, which is just commented out because we're not using it. We could also define set error message or set warning message here. And it's important to keep in mind that the variables defined in the first 4 tabs of this window are not accessible from within the C declarations window here. And this is because this window is where we specify our include statements, which will get placed before the variables, which we define here once the C code is generated for the state machine during the execution. And then if we go below here, we see that this is the hierarchical transition order, which I mentioned, which basically decides which of the transition gets executed, whether it's the one that's stemming from the substate or the superstate. We have a sample time that could be specified, and this determines how the state machine is executed. So 0 means continuous, meaning that the state machine is executed every time step that the variable time step solver decides. We can also set a time period here, which basically will mean that your state machine is executed at every certain period, or it could also be defined by an external block, which would basically, the input of it would go into the input of your state machine block. We also have an animation button check mark here, which you will see in this demo model that I'm about to show you. And this is very useful for debugging your state machine. Essentially, when the option is checked, the simulation is paused whenever a transition fires, and the transition path, including the source and target state, is highlighted, as I will demonstrate to you. Let me open a different demo model. So this example model is a simple model that demonstrates an oven control. while the oven is in operation, there is a hysteresis type control that keeps the oven temperature within a certain tolerance band around a temperature set point by switching the heating on and off here. The temperature set point in this case is 100 Celsius, and it's defined by a constant block. And we have a safety measure where we ensure that the heating is always switched off whenever the oven door is open, which is defined by this manual switch here. The oven itself is modeled with a heat source, a thermal capacitor, and a thermal resistor, which dissipate the heat, and we have a thermometer here, which basically defines the actual temperature that's being measured in the oven. So the inputs then of the state machine are the actual temperature, the set temperature, and the state of the door, which is either open or closed. And the output of the state machine is the heating, which is either 0 or 1. If we open the state machine, which has the oven control, we see that there are a couple of states. There's a door open state, a door closed state, which is actually a compound state because it contains other states here. And basically, the default transition, which is taken at the first execution of the state machine, is branched with a junction here. The animation checkmark is checked, meaning that we will be able to see what exactly happens and what that means during the simulation. So let me open our scope and start the simulation by clicking Simulation Start. As soon as we start the simulation, we see that our simulation is running, but it's paused. And this is because this animation checkbox is checked. So currently, we are able to see which exact state and transition we are in. So you see that the state machine has ordered, we have entered through the initial transition. We have a junction component here which decided which state we're starting from, whether it's the door open or door closed state. Since the switch is closed, we've entered the door closed state first. We also have another initial transition here to decide the precedence of one or the other states, or sub-states here, or leaf states, and we're in the heating state, and this is because the actual temperature is still less than the set temperature, minus the delta T. So as you see, we don't see anything in the scope yet, but the way you go through the simulation while the animation checkbox is checked is using your space bar. So if I press the space bar once, you see that we see that reflecting changes on the scope here. So we're displaying the oven door state, which will just remain to be 1 as long as the switch is essentially closed here. We have the heat flow displayed here. So we see that the heat was on for some time and now it's switched off. Because you see here the temperature, we are displaying the actual and the set temperatures. The green is the actual temperature, and the red is the set temperature, which is dependent with this set with this block. And we have essentially entered now the no heating state. As you can see, we have highlighted, Plex has highlighted the heating state, the transition, and the no heating state, meaning we're now in the no heating state. So if I press the spacebar again, you will see that the scope again reflects the changes. We have now again entered the heating state because the temperature in the oven has been dissipated by the thermal capacitor and resistor, and the actual temperature has exceeded the set temperature. So we're trying to stay around 100 Celsius plus or minus the 10 Celsius band that we've defined in the parameters window, which I will show you. Essentially, this simulation will continue to go back and forth, plus 110 degrees to 90 degrees, which is plus or minus 10 from 100, which is the set temperature, until something happens, until there is another input to the system. In this case, it could be opening the oven door. So during the simulation, with the simulation on, let me double click on the switch, which will force the oven door to open up. So now, as soon as I press the space button, you will see the changes being reflected accordingly. You will see that we're now in the door open state. So we have essentially opened the door, and we're now in this state. And if I press the space bar again, we have completely fully transitioned from the transition into the state. And the simulation is just running since there's no inputs being given to the state machine. So what we can do now is close the oven door again and press the space bar, and you see that we've gone from the door transition back again to the initial transition here through the junction, and we've entered the heating, and then now we're in a no heating state. And again, we're going back and forth here. Something else that we can change on the fly that could be interesting is the temperature set point. So if I go in this constant block, I can change this to 90 degrees, for example, hit apply and OK, and without, while still running the same exact simulation, I'm just using my spacebar again to go to the next step to allow the solver to take the next step. And you can see that the red line has now decreased to 90 degrees, and my hysteresis controller will now try to be within 10 degrees of the 90 degree temperature set point. So that's mostly what I can speak to about this particular model. Perhaps I can also show you how some of these were defined. You can see that we have 3 input variables which are displayed in this order on the input side of the oven control block. We have a heating output variable. We have the delta T constant, which is defined here, and this is our band, remember? So this is the 10 Celsius, which is used in these expressions here in the transitions. We don't have any variables or C declarations in this model. So if I pause the simulation, one thing I can also show you is if I uncheck this animation checkbox, then the simulation will just keep running by itself. So I have just started a new Plex simulation, and as you can see, the states are no longer being highlighted, and Plex is just running a simulation by itself, which is not very interesting in this particular model necessarily. So let me open a different model, which is a little bit more power electronics related. So this model demonstrates a constant on-time control for a buck converter. The outer control loop computes a current reference from the difference between the actual output voltage and the voltage reference. And the inner loop uses a constant on-time control scheme where when the actual current becomes less than the reference current, the MOSFET will be switched on for a fixed duration. And after the FET was switched off, it must remain switched off for a minimum duration before it can switch on again. So we see that the current compensator here was implemented using a state machine. If we double click here, we see that we have the current error being the input to the state machine, and the actual MOSFET switching signal as its output. When the on state is entered here, the enter action will set the MOSFET switching signal to 1, which is S, and then exactly T on seconds after the entry of this state, this transition becomes active or fires. This causes then the state machine to transition to the off state, where the output signal S is set to 0. And then again, exactly T off min seconds after this event, the state machine is then executed again, and the timer event after T off becomes active, after which this transition is branched with a junction, and if the input signal, the current error is already greater than 0 at this instant, the state machine transitions directly to the on state again. If the I error is not greater than 0, then the state machine transitions to the waiting state, ready for on, in which it remains until the current error becomes greater than 0. So if I actually simulate this by clicking Simulation Start, you will see that we've entered the on state. And if I cycle through with my spacebar, we see that we're now in the transition between the on and off state. Once I press space again, we're between the off and the on state, and you can see that the appropriate changes again are being reflected in scope. If I zoom in a little bit. And so we keep cycling through with our spacebar as our output voltage grows and our inductor current initially grows and then reaches steady state eventually. So something I can show with this model, this might be more interesting, to end this simulation and actually uncheck this animation box. Click OK, and then say Simulation Start to just let Plex run on itself using the state machine block still, but without using the animation portion of it. And you can see that basically all of these steps would be highlighted going through all of these different states using the state machine and producing the same result in the end. So something else I could mention is that whenever Plex runs a simulation for a model that has a state machine in it, the C code for the state machine is generated internally, then compiled and loaded to memory. The C code generated from the state machine incorporates everything in it, including the actions that you specify here in the new model. During the simulation, the code is executed to operate the state machine. And if you have a Plex Coder license or a Plex Coder trial, which are also available, it is very easy to generate code for a subsystem which contains a state machine block. And then that allows you to look at the generated code. So you will see the C and H files for the particular Plex model that you've generated the C code for. So you will find this code pretty readable, and it will contain a large switch statement that decides which actions to execute, which transitions to take, etc., based on the current state. So this is something that is currently possible with the Plex Coder. This concludes the presentation portion of the webinar. For more information on the state machine, you may refer to the help section of the block, which is accessible by right-clicking here and clicking help, or you can also access it by clicking the question mark here. I will now see if I can share and answer some of your questions with everyone. Feel free to ask more questions right now. Okay, I see the first question here. What is the difference between state machines and C scripts? Okay, so this is something that I referred to in the beginning. Essentially, state machines are or should be theoretically easier to use because they offer a graphical interface to design them. They are more intuitive, maybe, and visual, especially with the help of this animation checkbox that we have, thus making a state machine maybe an appealing alternative to a C script block. I do have to say that C scripts, on the other hand, are more old school, so to speak, more flexible and open, offer more control over the interaction with the Plex solvers. Something C scripts can do that state machines cannot do in our case is that C scripts can also integrate continuous states to implement an integrator, for example. So they're executed during minor steps as well, not just the major time steps. Is the Plex state machine executed continuously? So our state machine can be executed continuously, which means in each time step, which could be irregular as well, or it could be executed at fixed time steps. And this is decided by this sample time parameter here. So this option, you can feed continuous or discrete signals into a state machine for it to react to external events and output discrete signals, as we have seen. You should note that the state machine is only executed during the major time steps, as I mentioned, and the variable time step solver then handles the placement of the execution steps on the time axis arbitrarily, so as Plex prefers. So can there be more than one transition in the same time step? No. So there are never multiple transitions executed within the same time step, and there's only one transition essentially during one time step, or there could be no transitions, if none of the parameters or triggers or conditions evaluate to true. You could also note that a state is also never entered and left in the same time step, so only one state action is executed in one time step. For example, if I had an enter action, a during action, and an exit action specified here, Plex would spend one time step in the enter action, then as many time steps as needed in the during action section, while the execution flow remains here, and then one time step in the exit action. Let's see. These inputs, outputs, these tabs over here can only currently be scalars. They cannot be vectors. This is something that we're considering adding in the future. And if you would like to use vectors with a state machine, then we would be interested in learning for what particular reasons and for what applications. So please let us know if you'd like to use vectors here. So there's another question about the difference between the trigger and the condition when I had the x equals 0 part. So let me go back to this model here. So this is the part of the model that I was highlighting. Essentially, they are both x greater than 0, but they execute in different ways. So the fundamental difference here is that the implicit trigger, which is this guy here, will only execute at the time step when x becomes greater than 0, which means that if it was less than 0 during the previous time step and becomes greater than 0 at this time step, that's the step at which this particular transition, this particular trigger, will be executed. If we place this x greater than 0 into the condition field instead, then this now becomes a condition, of course, and this will be executed at any time step or at all time steps whenever x is greater than 0. So essentially not just one point, but potentially multiple points if x remains to be greater than 0. Are there any additional tutorials or examples to try out? And will the video be available afterwards? Yes, so we are currently recording this, and all of the attendees, and in fact all of the people who registered for this webinar will get the link to the recording. About the tutorials and examples, yes, we can share those with you. Please contact us for those, and we can email those to you. And another question is it possible to simulate frequency domain? So it's not very clear to me whether you're referring to a frequency response, in which case we have small signal analysis tools which are, generating body plots, or if you're referring to monitoring waveforms in the frequency domain, which we have an FFT function built into the scope for. So both of these are obviously covered and possible in the Plex, if this is what you're referring to. And you will find the FFT button within the scope. This is it here. And the last question I see here is there a separate license for the state machine block? No, so this state machine block comes with Plex. It's built into our library browser as long as you have Plex 4.0 or later version installed. So we introduced the block in Plex 4.0, and we've added the junction button and also time-based triggers in Plex 4.1. So you really want to have probably the most recent version to use the state machine block. And you can find it by typing in state machine, and you have it here. So a great way to learn more about a state machine is, again, by going to this help window. You can right-click here and click Help, and this has loads of information, and some of the details that I haven't even covered here. So please look here as well. And actually, this explains the 2 demo models which I showed today. So thank you very much for everybody's time. I hope that you will use the Plex State Machine block and that you're successful with it. We are happy to support you in any way we can, and I hope that you'll continue to attend the future webinars like these. We would also appreciate if you provide us some feedback via the survey that you will see after this webinar ends. It will also be sent to you in the email, I believe. Thank you very much again, and until the next webinar, until next time.